I understand this is like a quite wide dynamics crowd, and I'll try to just please interrupt me whenever I'm not sure like which kind of things are like known to all dynamicists and which kind of things are more to special kind of dynamicists. So let me just try and start. Basically, there'll be like there are three. Like this is a work. First of all, this is a joint work with Arie Levit. And maybe I can call this the title of this talk. I can draw a triangle. This is there are basically three notions that in this work we kind of understood that are related. One is group stability, which I'll introduce in a moment. Another one is something from topological dynamics. And the third will be character theory. Now, and somehow they're all related. Actually, in a sense, the core of this work is the character theory, but it's the most technical and hard to explain. So I will kind of more focus on this connection, even though there'll be underlying a lot of character theory that I'll kind of suppress. Let me try to just introduce each of those topics separately first. So group stability basically asks. So group stability. Basically, you have a group G. G is a group. So is every and I'll keep it vague for the moment, but at some point I will define almost homomorphism of G close to an actual homomorphism. Okay, so what is an almost homomorphism? What you should think of is that, so for example, I won't define this yet, but this, I would say that G is stable if this phenomenon occurs. Let's take an example. If G is Z2, then, and let's say the target group is, let's say unitary group. So we have a map here. So I'll say that F of G, and let's say this is generated by the two standard elements. Maybe I call them E1 and E2. So F is let's call it F, a delta almost homomorphism, or let's keep it without quantifying it. So just is a almost homomorphism. So what is a homomorphism from Z2 to the unitary group? It's choosing two unitary matrices that commute. This is an actual homomorphism. You need to choose two unitaries, and they need to satisfy the relation of being commuting. But an almost homomorphism means it means that you need that FE1 and FE2, that their commutator in norm is small. Is close to 1. I'm sorry, is close to 1. This is a group commutator, so this is small. So it means the matrices almost commute in the sense that their commutator is not precisely 1 like it is for commuting matrices. So commutator here, I mean like A inverse B inverse. It's the group theory commutator. It means if it were an actual homomorphism, then you know that it would those two matrices would commute. But since it's only an almost homomorphism, we only say that they kind of like almost commute. And then you ask if, so basically when you take this question of group stability and you restrict it to the case of, let's say, Z2, you get a very interesting question in linear algebra, which says, if two matrices almost commute, can I just slightly perturb them, slightly fix them to matrices that truly do commute? Turns out that this question is very subtle, and it actually depends on which norm you choose. And for certain norms, even though all norms are equivalent, but for some reason, because when you let n go to infinity, then the norms actually diverge from each other, and it's actually a very interesting question. So this is just something in the background that I'm now putting about group stability. I'll go back to it, of course. I want to now, this is like some kind of motivated question, but now I want to go about to now talk about topological dynamics and explain this part. So I want to, what do I mean by topological dynamics? I mean that there is a X, a compact, metrizable, or let's just say metric space, and there's some transformation T, which is a homomorphism on X. So the pair, the pair is a topological dynamical system. Sometimes actually I will have not just one homomorphism. Sometimes I'll have G, an action of G of a group G on X by homomorphism, and then I have a different dynamical system with like not just one time parameter, but like a group of parameters. So this is what I call a topological dynamical system. And I want to start with the following definition. Or before the definition, I want to just talk about topological dynamics. So usually when you have such a system, you're interested in dynamical properties. Maybe the first things you want to study is fixed points, of course. And the next step would be not fixed points, but periodic points. Okay, so periodic points, by periodic points, I mean periodic points means points in finite orbits. Okay. These are periodic points, and of course, what you can ask is, this is a general question that you can ask: are periodic points dense? Okay, this is like a classic question you might ask in a dynamical system. Let's give an example where this is the case. So if X is the torus, which also we can identify as Rn mod Zn. And let's say G will be the automorphisms of the torus as an abelian group. The torus is an abelian group, and the group of automorphism, of course, acts on it by automorphisms. So what you can show is that the periodic points in the torus are exactly the rational points. This is not hard to see because automorphism must take a torsion element of the group to a torsion element, and the torsion elements are exactly the ones with rational coordinates. So it kind of preserves so each rational point will be a periodic point, and this is exactly this, which is dense in of course in the torus. Okay, so this is a phenomenon where the periodic points are dense. Non-example, for example, will be maybe irrational rotation of a circle. Why non-example? Because no periodic points at all. Right? Great. So this is, I think, a very standard question that one asks in a dynamical system, but I want now a question which is, I think, just as much as interesting, but for some reason less shown in the literature, is going to probability measures on the space and asking a similar question there. So I'll always, when I do this notation here, I mean Borel probability measures on X. Okay, this is my notation. And when I do this, I mean the probability measures which are fixed by G. In other words, G invariant Borel probability measures. And sometimes I'll also want to talk about finite periodic measures. So this will be which are finitely supported. So finitely supported, I really mean finitely supported. I mean it's supported on it's atomic measures that are supported at just finitely many points. Okay, and so an important definition here is the system Gx has dense periodic measures, dense periodic measures, if the space of G-invariant probability measures in X, which are periodic, so they're just finitely, like very boring probability measures, if this is dense in the space of all probability measures, invariant probability measures. And dense here, this is a weak star topology. So mu n goes to mu if mu n f goes to mu f for all continuous function in our space. Is this good? Okay, so this is a definition which I want to study. And of course, everything is motivated with I'm kind of hiding it now from the original question of stability, of group stability. And soon I'll connect this with stability as well, okay? Maybe let's give some examples. So let's take again the example of what I said before. G is the automorphism of the group of the torus. And this is acting, of course, on the torus. And we said this is Rn mod Zn, and some of you probably know that the group of automorphisms of the torus is exactly GL and Z. Well, the reason is because it's not hard to see. GL and Z obviously acts on Z to the n, just by linear transformations. So the automorphism group of Z to the n is GL and Z, and this is just the dual, the Pontryagin dual of Z to the n. So if it acts on Z to the n, it will act also on the dual. Or alternatively, GL and Z acts on Rn, and since it's also preserves Zn, then it acts on the quotient Rn mod Zn. And this is actually the whole group of automorphisms of the torus. And it is a fact, it is not a trivial fact, but that the probability measures on the torus, which are invariant under all automorphisms, and here let's just say ergodic probability measures. This is exactly there's of course the Haar measure on the torus, and many periodic measures. In other words, if this is the torus, the two-dimensional torus, then of course the Haar measure is invariant under automorphisms. But for example, if I take this half, zero, half, half, zero, half, you can see that this is also an orbit on the torus. So you have an invariant measure, which is just uniform measure on these 3 points. This is an example of periodic measures. But then you have also thirds. This is another measure, and quarters. And what you can show is that they get more dense and more dense. And in particular, this is an accumulation point. The Haar measure, you can approximate it by those periodic measures with just taking more complicated periodic measures. So this is an example where we have, so this has dense periodic measures. Again, because when you want to check if you have dense periodic measures, it is enough only to consider ergodic measures to show that any ergodic measure can be approximated per periodic measures. And here, when you have a measure classification like this, which is usually not the case that you have such a nice measure classification, it's very easy to verify it because the periodic measures are already periodic. There's nothing to show. And the Haar measure is the only non-periodic measure. And this is indeed a limit of periodic measures. Do you have questions so far, by the way? Just feel free to stop me if anything's not perfectly clear. Great. Now I want to start a little bit to relate this to stability, because I think it's completely unclear how all of this is related to the question I asked before about two matrices almost commuting. So I want to make another definition called so maybe I'll just ask a general question: is which dynamical systems have dense periodic measures? So this is just a general question that sometimes it was studied for many systems. It's not like something completely new, but for some reason you don't see it a lot of in the literature. But I think it's related to a lot of stuff, and now I want to relate it to a stability property of dynamical systems. So I will say that the dynamical system, and for now let's take one transformation instead of a group of transformation. Let's just take, I have X and I have this T, this homomorphism in X. I say this is orbit stable if for all epsilon exists delta such that for any delta almost orbit, such that any delta almost orbit, and I'll explain what I mean by that in a second, is epsilon close to an actual orbit. And I'll explain what I mean by this in a second. Okay, but this is just for something is almost an orbit, then it's close to an actual orbit. It starts to remind us of this group stability thing. What do I mean by an almost orbit? So an almost orbit. So what is an orbit? An orbit is, of course, a sequence of elements in the set, such that Txi equals equals xi plus 1, where I is 0 till n mod, okay, let's call this 1 mod n, right? This is an orbit. It's exactly what is an orbit, but what is an almost orbit is to say that the distance between these 2 points is smaller than delta. This is a delta almost orbit. Is epsilon close to an actual orbit means that there is an actual orbit, y0, yn, which is an actual orbit. So here really I equals 0 till n, so 1 mod n. So this is an actual orbit, but which is very close to the original orbit. So the distance between xi and yi is smaller than epsilon. Okay, so if you have an almost orbit and you want to kind of change probably the initial point, maybe change it a little bit such that now it will close into an orbit and will stay all the time close to the original point. And okay, is this definition clear? Right. It might, I don't know if you guys know of a different name for this. I'm sure that it was studied in different contexts. I call it orbit stable, but I don't know if there's a better name.
Actually, I do know a similar name, shadowing. I think it's
yes, exactly. Shadowing is very, very related to this. Yes, thank you. So, right. So you would say that that if I understand correctly, you would say that this is a shadowing of this.
Yeah.
Right. Yeah, exactly. So maybe I'll just write the word shadowing. Thank you. Now, here's let's start with the following proposition. if Tx is orbit stable, then Tx has dense periodic measures. Okay, let's prove this. So dense periodic measures means that every invariant probability measures is a weak star limit of periodic measures. So I start, of course, with let mu be a probability measure on X, which is invariant under T. And of course, I can assume ergodic. This is just by Krein-Milman, I can assume ergodic. If you show something for the ergodic one, these are extreme points, you'll show it for all measures. So the first thing I'll do is by ergodic theorem, Birkhoff ergodic theorem, for mu almost every X in X. So the empirical measures, so here I take K equals 0 till N, I average it, and I take the Dirac measure on TKX. So these are the empirical measures of step N. These are, of course, periodic measures, just finitely many atomic measures. This converges in the weak star topology to mu. This is exactly I don't know, maybe sometimes you see the Birkhoff theorem with functions, but this is exactly the same thing, because if you now, what does it mean weak star convergence? It means that when you evaluate these measures on continuous functions, you get this convergence. And when you evaluate in continuous functions, here you get just the values of the average of the function over the iteration in time. And here you just get the space average of the function. Great. So it seems pretty good. Like this is a periodic measure. We without even any assumption, this is a periodic measure, and we already found that we already approximate mu with a periodic measure. But of course, this is not an invariant measure because it starts invariant, but then at the level of n step, of course, the next if I take the next iteration, there's no reason it will go back to the point X. Okay, so these are periodic, but not T invariant. So what can we do? By Poincaré recurrence, exists K large enough, or exists let's call this mu n. So exists n large enough such that okay, wait, first this happens for almost every X. So I want to choose such an X. I'm fixing now an X. Okay. So by Poincaré, this exists n large enough such that T n X is very close to X. So now what does it mean? Hence, X, Tx, T squared X, T n minus 1x is an almost orbit. Right? Because actually, this is to be an almost orbit means that this point, when I iterate with T, should be close to where it should be. But here it's actually it acts as exactly like an orbit all the way. And just at the last point, instead of going back to X, it goes back to a point which is almost X. So this is a delta almost orbit. Now, by orbit stability, exists Y in X such that Y ty, t squared y, tn minus y. So first of all, or let's just say there exists, let's just say an orbit, is orbit stability exists in orbit, y1, y2, yn, such that the xi, yi is small. Now, let's denote this by mu. Let's take the measure mu n tilde to be just the sum of delta yi. I equals 0 till n, 1 over n plus 1. So since this is very close to this, then mu n tilde is very close to mu n. Right? Mu n was just the empirical measure of these x, and I just moved everything a bit to get this orbit. So mu n tilde is very close to s, and it is periodic, just like mu n was, and also t invariant. It is t invariant because it is an orbit. This goes to this goes to this, and this goes exactly back to this. So hence mu n tilde and what's more important is and mu n tilde converges in the weak star topology to mu. And this is because mu n converges to mu, and mu n tilde is arbitrarily close to mu n. We found dense period. We showed that this has dense periodic measures. Okay. So orbit stability implies dense periodic measures. Let's give an example. Now, this can help us find systems which have dense periodic measures. By the way, Eran, do we take a break usually at like after 45 minutes or so, or?
Depends on your preferences.
Well, I don't mind, so I guess it depends on your preferences. Do you have any preference, or?
I don't mind. Does anyone else prefer a break, or? Okay, so if not, you can.
Okay, I'll just see. I'll finish this dynamical start, and then maybe we can take a 5 minutes break, and then I'll continue to group stability and show how it's related. But before that, I just want to talk more about these properties that we talked about and see some examples. So example, and the example is Bernoulli shift. So here x is 0, 1 to the power of z, and t is the shift. So this is a topological dynamical system. This is a compact space, and T acts on it by homeomorphism. And I want to show that this has dense periodic measures, which maybe at first would sound like a hard task, because you need to start saying to consider invariant probability measures on the Bernoulli. And they're like there's a lot of, it's not like you have a measure classification for these, so it would be very hard to start analyzing this measure and showing that it is a limit of periodic measures. But to show that it's orbit stable is much easier. Actually, it has sometimes it's called orbit closing lemma, what I'm now going to do. So what is an orbit in a finite orbit in the Bernoulli shift? It means a string. If I have a string, what is a periodic point? It means that I have some kind of a string, and the and then I just copy this string. It's a period, so it's periodic for the shift, right? What does it mean to be almost periodic? It means that after I shift it like n times, I get a new string which is not exactly the same string I started with, but on a large part of the space, it looks the same. So it's kind of almost a periodic string. But it is very easy, if you have an almost periodic string, it's very easy to turn it into an actual periodic string, because then I can always, so what is an almost periodic string? It means that maybe the next one is not exactly here, maybe it's here 1 1 instead of 0 0. I don't know. So there's like some mistake. But then I can fix it, I can change it if it's so much looking like a periodic point for such a long string. I can just take this and kind of erase this and fix it. It's very easy. If you have something which is almost periodic, I can just take a large window where it seems periodic and then just do copy paste to that. And because for such a long place it was periodic, so I didn't change my point a lot. I just, because it's the metric comes by how much, it's like a local it's like in cylinders. So this, in other words, that Bernoulli shift is orbit stable. It's orbit stable, hence has dense periodic measures. And another example is when X is the torus and T is an automorphism of the torus, which is hyperbolic. So in general, like hyperbolic systems tend to be orbit stable. They have like this shadowing property is many times shown, for example, for hyperbolic systems. There's actually a stronger notion called specification that I don't know much about, but this is much stronger than the shadowing. Maybe you heard of it, and axiom A differ. There's a lot of like notions that are kind of all related somehow. So when you have an hyperbolic system, by the way, like I said, this is GLNZ. So as a matrix, being hyperbolic means that the matrix T as a matrix has eigenvalues, is diagonalizable with eigenvalues not in the unit circle. This is just a characterization of what is an hyperbolic automorphism of a torus in terms of the matrix. Okay, so these are different kind of examples of situations. Mainly what I'm interested in is when X in general is a compact abelian group, like with the torus, and also like with the Bernoulli. This is also a compact abelian group, because this is a group, this is Z-mod 2, and this is by automorphism. So X is a compact abelian group, and T is an automorphism. And by the way, there's a nice theory of these systems. These correspond, because if you take now the Pontryagin dual of X, then it is a discrete abelian group. And the action of T will be, this will be a ZX module. So the action of T corresponds to the action of this generator, sorry, X and X inverse. So there's a very nice correspondence and between automorphisms on compact abelian group and modules over this ring. And there's a lot of studies actually about these kind of problems, and I would want to understand when dense periodic measures, what does it correspond to here? Because this, I think, will help understand which systems have dense periodic measures. I think now it's a good time for a break because I kind of finished this kind of just dynamical stuff unrelated really to the group theory. And then after the break, I want to go back to group theory and try to relate it to the dynamical systems and show some new results about group theory using. So these examples are not just examples. I'm going to use each of those examples. I'm going to use it to do something about group theory.
Okay, great. So let's take a 5-minute break.
Yeah. Great.
Okay.
Okay, great.
Wait. Is this connected or not? Okay. Can you talk for a moment? I can't see if I.
Yeah. Can you hear me?
Yeah. Okay. For some reason, I hear you from the.
Never mind. I'll just talk without a. Wait. I understand what I should do. 1 second. Sorry.
Okay. Now it's probably better.
Can you hear me now?
Yes. Now I hear you well. Because,
Great.
Great. So let's continue. And let's start a new subject, and this is group stability. So so suppose I have a group G. Or okay, so G will be some group. G is a group. So definition, almost, so an almost homomorphism of G, or maybe I want to do it a bit differently. So I have a group G, and suppose it is generated by some generators and some relations. Presentation of groups. So for example, if G is Z2, then this will be E1, E2 with the relation that E1 and E2 is trivial. Okay. Is this the notion of group presentation of groups? I assume is known. Yeah. Okay. Now, so what is in so definition? G is and I use here the notion Hilbert-Schmidt stable, because there are many different notions of stability, and this notion will be related to matrices with a certain norm called the Hilbert-Schmidt norm. So Hilbert-Schmidt norm on UN is the following. What is the norm of a matrix A in the Hilbert-Schmidt? It is the trace of A star A, and I normalize it by 1 over n, and I take the square root. This is, by the way, equal to the sum of the entries Aij squared Ij 1 over n square root. It's like some kind of like Euclidean norm of matrices. Okay, this is a norm. So G is Hilbert-Schmidt stable if for any epsilon, it's very similar to orbit stable. If for any epsilon exists delta such that any delta almost homomorphism, and like before, I will keep this for a moment undefined, is epsilon close to, so any delta almost homomorphism F from G to UN is epsilon close to to an actual homomorphism phi from G to UN. So what is a delta almost homomorphism? So what is a homomorphism? So a homomorphism, so sorry, this is not from F, it's from S, it's from the generators. So what is a when I have a group that is generated by a set S, of course, it's enough to specify for a homomorphism, it's enough to specify what it does to the generators. And for it to actually define homomorphism, I need the relations to be satisfied. Okay, so any delta almost homomorphism from S to UN, this means that for all R, in R, this is a word in group theory, this is a word in the generators. For example, it could be the commutator. So F of R is close to the identity. Okay. So if G is Z2, then R, this is Z2, this is E1, E1 and E2. R is just one generator, which is the word. It's like it's the formula X, X1, X1, X2. This is just so here it's demanding that the matrices almost commute. And saying that this is epsilon close to an actual homomorphism means that phi, so actual homomorphism, so phi is a homomorphism. And phi is very close to F, so Fs minus phi S in Hilbert-Schmidt is epsilon close for all S and S. So a group is stable if, whenever I have an almost homomorphism, I can slightly change the this map to get an actual homomorphism. Okay. So example, three groups are stable. In a vicious sense, I mean, well, free group is generated by a set with no relations. So there's nothing to satisfy. So every map from the free group, from the generators of the free group to UN defines a homomorphism. There are no, every almost homomorphism is already a homomorphism. So this is very a boring example. But what about Z2? Z2 is also stable. This is a result by Glepsky. Which basically shows, i.e., if two matrices almost commute, then they are nearby matrices that truly do commute. And maybe a remark, if the Hilbert-Schmidt norm is replaced with the operator norm on matrices, then Z2 is not stable. And this is a beautiful result by Excel and Loring. And there's a very nice winding number argument that shows. I mean, showing that something is not stable, they mean they construct a almost homomorphism, and they need to show that it cannot be corrected to a homomorphism. And the way they do it, they kind of say, if it would be corrected, you could kind of draw a map in the space of matrices, and composing it with the determinant, you'll get some certain curves on the complex numbers. And with a winding number argument, they show that it cannot be corrected. It's actually a one-page proof, but it's really beautiful. Actually, I think it's the most beautiful, one of the most beautiful things that there are. So maybe I will put a link to this paper because I think you should see it. Let's see. That's it. I found it. Yeah, here it is. It's really you should look at it. It's just you see it's like three pages of paper, and the proof is just one page. It's really cool. Okay, let's go back. So what about other groups? So actually, this is considered a very hard question in group theory. So in dynamics, I think people are very used to ask those kind of stability questions of what happens when you change a bit to starting point. But for some reason in group theory, these kind of questions, only recently this research became like really like Alex Lubotsky, I think, is one of the people who the most advocated this in Israel, and it became it's also related to computer science and to quantum information and to many other topics, this stability. In a sense, it goes back to von Neumann in the 20s, where he asked, because for quantum mechanics reason, it's very important if two observables or matrices, they commute. And he's maybe the first one who kind of asked a certain type of questions. If two matrices almost commute, can they be fixed to matrices that actually commute? So this is a quite interesting question in group theory. And there are not many techniques to study it. It's very hard. There's not much, in algebra, we're used to things with a lot of structure, like homomorphisms. And when you have an almost homomorphism, it's very hard to analyze it. But what's nice is that there's a nice theory. So, like I said, free groups are stable. More generally, abelian groups. So Z2 and more generally, abelian groups are stable. But not much was known about this until a few years ago, where there's a theorem by Hadwin and Shulman that says an amenable group is stable if and only if every character of the group is a limit of finite dimensional characters. Okay, now let me mark all the words that I'm not going to define. So I'm not going to define what's amenable. but it's a nice class of groups. It includes a billion groups. It includes all solvable groups, for example. But it does not include the free group, for example. And also character I'm not going to define here. It's related to representation theory. So like what is a finite dimensional character? It is like when you take a finite dimensional representation pi and you compose it with a trace. This is what they call a finite dimensional character, and there's a more general object called characters of a group, that if you want to do a harmonic analysis on a non-abelian group, if your group is just R, then the characters will just be e to the I theta. You'll get like the standard Fourier analysis, but when the group is not R and not even abelian, there's a more general notion of characters that allows you to do a kind of Fourier transform on non-abelian groups. But I don't want to get into it. This is just a theorem that tells you how stability is connected to characters. And basically what me and Arie Levit did, we took this one step further and connected it to dynamics. So let me explain why. So take a solvable group. Take a solvable group. Because, okay, abelian groups are stable, but what about the next step is maybe to take nilpotent groups or solvable groups. And let's take a particular example. Let's take Z semi-direct product Z2. So what is it? So a semi-direct product, I mean that here, when I have it means Z acts on Z2. And instead of taking a direct product, I'm taking some kind of twisted product, so semi-direct product to construct this. And this is a group G. This is a solvable group. This is a two-step solvable group. And I remind you that this is GL2Z. So or let's take more generally. Why take Z2? Let's take A. A is an abelian group. Z acts by automorphism in this abelian group, and I formed a semi-direct product A. So this is an example of a solvable group. So here's a theorem by Arie Levit and myself, which is just actually this is a special case. Is that G is stable if and only if the dynamical system where the group acting is Z and the topological space is the dual of A. This is because this is discrete abelian. So for example, Z2, this is compact abelian. For example, the torus. So G is stable if and only if the corresponding this dynamical system has dense periodic measures. Corollary 1, Zn is stable where the action of Z defining this semi-direct product is hyperbolic. So like I said, the matrices that define the matrix Z acts on this by a matrix in GLNZ, and that this matrix has only eigenvalues which are not on the unit circle. Another example is the Lamplighter group. The Lamplighter group is a quite interesting group. I don't know if you've seen it before. It is the Reith product of two groups. So basically what you do is you take an infinite direct sum of this finite group, this element of two groups, and Z acts on it by shift. So I can form the semi-direct product. So this is called the Lamplighter group. The reason it's called the Lamplighter group is because this direct sum, you can think of it as in an infinite line, where at each point there is a light. And on each coordinate on the grid, there's a light, and there's a person here. So this is corresponds to this coordinate here. This coordinate is where the person is at, and at each step, he can move. He can turn on. So each light is on either on or off. He can turn on the light, and then he can move also to the right and move and turn on the light there and move to the right. So I mean, this group represents the space of states of this system, where the person can every time turn on a light where he has or turn off the light and move to a different step. So it's called the lamplighter group, and it's a very interesting group in group theory. We study this group a lot, and this is part of a corollary is stable. And why is it stable? Because here this is the abelian group A, and the dual of this group is exactly Z2, the product Z2. So it's exactly the Bernoulli shift. So because this, i.e. the Bernoulli shift, has dense periodic measures. So I'm showing you how the stuff we studied before, this is basically what we did. We realized that certain questions in group stability can be traced down to questions about dynamics. And then by studying the dynamics, we get the answers to those questions. Let me just finish maybe with one more example. That stuff I don't know. So these are examples that we do know, but some spaces we don't know. So here, for example, let's take the Furstenberg times 2 times 3 system. So what is this? Here, X is the circle, or R mod Z. And the group G is Z to the 2, or it's not a group here, but I have two transformations, basically. Okay, I'll just write Z to the 2 and cheat a bit. Where one transformation acts by multiplication of the angle by 2. So it multiplies the angle of the circle, and the other transformations multiplies the angle by 3. This is called the Furstenberg times 2 times 3 system. It's the group Z2 acting on the circle. And it's conjectured that the ergodic invariant measures are the Haar measure and the periodic measure. So if this is true, and this conjecture, of course, will imply the dense periodic measures, because if you know exactly all measures, it's very easy to show you have dense periodic measures. But of course, this is a huge conjecture, and nobody knows it's true. But a question that I find interesting is to at least ask if this weaker property of having dense periodic measure holds. So, this system, so a corollary, another corollary of what I said before, that this system has dense periodic measures if and only if the group Z squared semi-direct product Z to the 1/6, where the action is again by multiplication by 2 and multiplication by 3, is stable. So this is an example where we know how to translate it to a dynamical, this stability question, we know how to translate it to a dynamical problem, but we don't know how to solve the dynamical problem. There are actually many. I put the paper. I shared the paper with you, and you can see we have in the end of the introduction a list of questions. So there are many other questions that you can ask purely dynamical questions that if you solve them, then you actually solved questions in group theory straight ahead. So you're welcome to look at it. I think I'll finish here. I said basically all I wanted to say. That's it.
Okay, so let's everyone thank Itamar for his talk. It was very interesting. Are there any questions? Okay, so if not, let's thank Itamar again. It was a very interesting talk.
Thank you.
And I guess we meet again next week. Also, I should also state next week there's an Abel Prize talk. So if everyone is interested to come, please contact either Noy or myself. So that's it.
Will it be on Zoom?
Yeah, it will also be accessible on Zoom. Yeah.
Okay, cool. Great.
So see y'all.
Thank you so much.
Bye-bye.
Bye-bye.